Hi everyone, welcome to another class on the course on quantum theory of many-body systems in condensed matter. My name is Luis Gregorio Diaz, here at the Institute of Physics at the University of São Paulo. And in today's class, we're going to go over linear response theory and derive the Kubo formula for generic perturbations. And as an example, we're going to consider the dielectric response of a system of charges, and we'll calculate the Kubo formula for that case and how linear response occurs and how it depends on a charge-charge correlation function in this case. Okay, and we're going to use linear response in the following classes. Particular next class, we're going to consider the conductivity and the conductance in systems. All right, so let's get down to it. All right, so let's start with linear response theory and the idea behind linear response. So let's say we have a Hamiltonian H0, okay, and that's our reference Hamiltonian, if you wish. And then at some time that I'm calling T0, we turn on a perturbation, which I'm calling delta H. And this perturbation might be itself time dependent. So what's going on here is that the Hamiltonian then will be time dependent for the system. Before T0, there was only H0, and there was the Hamiltonian of the system. But after T0, for T larger than T0, then the whole Hamiltonian is this H0 plus this delta H. Okay, so before T0, we refer to the situation as the equilibrium situation. So we might know even the spectrum for H0, so we can calculate the expected value for a given operator A, right? We know the partition function, we know the spectrum, and we know also the density operator here, and we can take this trace and calculate the expected value at equilibrium. Notice that here we're using the canonical ensemble to calculate this. So this is known, right, is our value of equilibrium. And the question that we want to answer is what happens to this expected value when I turn on this perturbation. So, if this perturbation is small, it's reasonable to suppose that the expected value will not be much different than the one at equilibrium, but there will be this correction, which might be time dependent, and that will give me time dependence to the expected value as well in this what I'm calling non-equilibrium. And we want to calculate this correction up to linear terms in the perturbation. That's why we're calling this linear response, right? So it's as I said, this is not very large. So we don't do anything drastic to the system. We add a perturbation, and you want to see how the system responds given this small perturbation. So what we're going to derive now is the so-called Kubo formula, which gives it precisely what is the expression for this in terms of delta H up to first order. And it turns out that this correction is a correlation function where between A and delta H, and both written in the interaction picture. Right, so I'll try to remember to put here a link to the class where we define the representations in quantum mechanics, in particular the interaction picture, where I evolve the operators with this H0 here. Okay, so let's see how we arrive at this formula, the Kubo formula, starting from this. Okay, so we're at the blackboard now. So let's first define what we want to calculate, okay? So we'd like to calculate this quantity, expected value of a quantity, function of time, for t larger than t0, where at t0 we have the interaction turned on. Okay, so let's first define what happens for t less than t0. Okay, that's our reference, right? For t less or equal than t0, what you have is this. The expected value of a is simply 1 over the partition function, right? So we have the Hamiltonian h naught. We know its spectrum, okay? And I'm calling this. So we know that. So we know the partition function, which is just sum of alpha e minus beta e alpha naught, right? So the idea here is that the system was in equilibrium, right? Thermal equilibrium with, say, a thermal reservoir, and then there's these Boltzmann weights in the energy levels, right? And we have this is well defined. We know that. So any expected value here for this will simply be given by this, right? E minus E beta E alpha 0 trace over A. Okay. Notice that even if I have, say, at a time equals a time less than 0, and let me write this in the Schrödinger picture. And this is, okay, this is the equilibrium value. So in the Schrödinger picture, so what's going to be the time evolution of these guys for t less or equal than t naught? This is going to just be E minus I h naught t, right? Up to t naught. Even at t naught, let's even say, let's put it to equal. You're going to use this. This is going to be E minus h naught t naught from the value at 0, say, which is perhaps this. The spectrum doesn't change, but let's say. So even if we want to calculate this expected value with this time evolved states, I'll still get pretty much the same, right? Because this would be simply E minus E h alpha naught t naught alpha, so it's just a phase, and everything here happens. So for any time between 0 and t naught, the expected value of alpha or of A is simply this, the equilibrium value. But now we want this guy, okay? So what we want to do is calculate this in linear response, right? So what we're going to write is, I'll still use the same distribution, right? I put my system in contact with the thermal reservoir back there, say at time t equals 0 or something, right? So it was still in equilibrium in terms of thermal equilibrium, still there. So the weights, the Boltzmann weights should not change, at least if the perturbation is small, okay? So I still get this. So this is in linear in the perturbation delta H minus beta E alpha 0. But now my states might evolve. So even if in the Schrödinger picture this would be alpha of t, where this evolves not with H, but with H plus, with H naught, but with H naught plus the perturbation, right? So this is for t larger than t. So that's the effect on the expectation value of alpha, is that now I have this time evolution with this perturbed Hamiltonian, okay? So this is what I want to calculate. Now, it turns out that, and of course, that alpha of t in the Schrödinger case is related to alpha at t equals t naught by the time evolution, but now with h, t minus t naught, alpha at t equals at t 0. Okay, so that's an important point. Now I'm evolving from t0 on with h, and that's the difference that I have. All right, so let's write these guys in the interaction picture for the reasons that make the interaction picture interesting, which is when I have something like this. Okay, then in the interaction picture I'll have the states, the time evolution of a state I equals a time evolution operator t naught, we saw that in the class, times the evolution of this sometime t0, okay? And I know how to relate this with this guy. I know that alpha t0 at interaction picture is e I h naught t naught alpha t naught in the Schrödinger picture. All right, and of course the operators also evolve with time. So an operator in the interaction picture like this is given by e h naught t a e minus h naught t. So it evolves with h naught, which we know, right? Which we know the spectrum at least. Okay, so now this is all interaction picture. And if delta H is small, we can approximate this time evolution operator as this, right? ut t naught approximated to 1 minus I, we're taking h bar equals 1, but this integral of the perturbation written in interaction picture as a function of time. Okay? All right, so let's now calculate the expected value. Now, essentially calculate this expression and put it in the interaction picture. And we know that, you know, how to write, we can invert this, and any operator in the Schrödinger picture is going to be e minus I h naught t times the state at the interaction picture. Okay, we know that from that previous class. So let's write this. Okay. There. So we have a of t equals 1 over z naught, sum of alpha, e minus beta e alpha 0. Then there will be the cat in the interaction picture here. Alpha t, there will be this e plus h naught a e minus h naught t, so this is also interaction picture, and this is precisely, not surprisingly, the operator a in the interaction picture. Okay, all right, so everything is good. I changed the pictures. It doesn't change my expected value. So let's keep on. And now I'm going to put these guys in terms of the time evolution operator. So I still have this sum over alpha e minus beta e alpha 0. And then I'll have at t0, the interaction picture, times u dagger between t and t0, a in the interaction picture at t, okay, then u t0 alpha at t0 at the interaction picture, which we showed. Oh, we haven't showed yet, but let's show it now. So who is this guy? Okay, this guy is simply, right, the Schrödinger operator at t equals 0, and we know that the Schrödinger operator at t equals 0 is e minus e h naught t0 times alpha. So this e minus I h naught t naught times this gives me 1, and all I'm left is with the state alpha, which is the state in the Schrödinger representation at t equals 0 if you want, okay, which is precisely this. All right, so this gives me an interesting point that this would just give me an expected value at equilibrium, all right, this of whatever's in here in this approximation. Okay, so let's now expand this guy, and I'm going to use this. So this one is going to be 1 minus, or 1 plus, right, I integral in dt prime delta h t prime, and this one is going to be 1 minus I dt prime delta h t prime. So to first order in delta h, what we have this. So first, let's remember that these guys are alpha, and this is get alpha. We just, right, found that. So let's go one step further. One step further is to first order in delta h. This is going to give me what? 1 over 0 sum over alpha e minus beta alpha e alpha alpha a alpha, right? When I have 1 and 1, plus what? Plus 1 over 0. Let's take, say, this term here and 1 here. So I don't want a delta h square. It's going to be 1 over 0 sum over alpha. Yeah, I'm going to just write this once. Okay, I'll have an alpha here, and I'll have this first integral minus I integral in dt prime. Then I'll have AI at t delta h at t prime. Okay. Now there is going to be a second term, which is this I plus I dt prime. Now there's going to be a delta h at t prime times the I, the a at t, and that's it. All the other terms are order delta h squared. Okay. Now notice that this term is simply the equilibrium value. This is weird. Let's do it like this. This is the equilibrium value, right? This here, right there. The equilibrium value. So this is in this approximation. So A of t approximation is A calculated in equilibrium. And this is also going to be a expected value at in equilibrium of what? Of whatever's in here, which is, let me write in this minus I, the integral from t naught. The limits are very important here, okay? Because I can only start at t naught. That's when I turn on my interaction. Yeah, remember t is larger than t naught. dt prime times the commutator of A and delta H, because there's going to be a minus sign here, okay? The commutator of A in interaction picture at time t and delta H at time t prime. All right. And I can rewrite this in the final form, which is to first order A naught minus I integral t naught to t dt prime times this. Oops, sorry. This is delta H calculated in equilibrium. And this is the Kubo formula that you want to derive. And of course, this is for t larger than t naught. So this we will have, and of course, t is larger than t naught, so, and t is always larger than t prime, so this is like a retarded correlation function, okay? So yeah, so that's, and this is like a retarded correlation function. We'll go back to that. But this is the Kubo formula we want to derive in linear response, only keeping linear terms in delta H. Okay, so let's go back to the slide. All right, so we showed this, that the expected value of A at time t equals the value of the equilibrium minus this integral, that runs from t0 to t, and this is dt1, right, or dt prime in the notes that I had, where A is evaluated at t, the final time, and delta H is evaluated at t1, which is the integrand, okay? Now I can turn this into a retarded function, a retarded correlation function, because the only thing that matters here is that t is always larger than t1 in this integral. By this definition, that's precisely what is going on. So I could take this integrand from t0 to infinity and adding a theta function, theta t minus t1, so that whenever t1 is larger than t, this is 0, and when t1 is less than t, this would be resulting in this integral. So that's how we're going to define, and we're going to define actually the difference between the expected value at t and expected value of 0 as precisely this integral of a retarded correlation function here with a theta of t minus t1. So let's see how does that work. Okay, so this is precisely it. Here I added these theta t of t minus t1, right? And I should put the minus I here in front. The correlator is still here. So this is truly a retarded correlation function, similar to those that we defined earlier in another class. I tried to remember to put a link to that class where we defined the retarded and advanced correlation functions. And so I'm writing the response, right? The difference between the expected value at t and expected value at equilibrium as the integral of a correlation function. More interestingly, and as we discussed in that previous class, that correlation functions of that sort usually depend on the difference between t and t1. So we can take the Fourier transform of those correlation functions, and this would be very, very important and useful, especially if my perturbation delta H, which might, as it's indicated here, depend explicitly on time, be written in this form, which is an operator times a function, right? So if I do that in the frequency domain, when I take the Fourier transform of this would be, the result would be a correlation function between operators A and B, the retarded correlation function, times the Fourier transform of this function. Okay? And there is also the special case where the perturbation is itself proportional to operator A itself, meaning that this B here is equal to A. In this case, this correlation function is usually called the dynamical susceptibility associated with operator A. And here there are a couple of examples where we want to, of course, measure the response function of an operator in a case where the perturbation is proportional to the same operator. So charge density, for instance, is one case. We're going to do an example in this class, the so-called dielectric response, and this would be then the charge susceptibility, but could be the spin density or the current density, and then I would have these susceptibilities. Here is usually not called a susceptibility, it's called the current correlation function, and we're going to see how to calculate this, or how does that work when we calculate the conductivity in linear response. But let's see how we arrive to this case when you write in these correlation functions in frequency domain. So let's go to the blackboard. So let's calculate the Fourier transform of this correlation function then. We learn how to do that. We have to first use the fact that this depends only on t minus t1 or t minus t prime here, and then we take the Fourier transform such as this. Notice that in order to define the Fourier transform, we need to take t0 here, right? We want to for this integral to run from minus infinity to infinity. So we're going to take t0 to minus infinity. what does that mean? Well, it means that the perturbation was applied at minus infinity, so it was there all the time. Okay, so this is an artifact so that we can have the response function and frequency domain well defined, but it also means that we are disregarding the transients, right, from when you actually turn on the perturbation. You have the equilibrium there at minus infinity, and then you turn it on, and everything evolves with time from there. Okay, so doing that, and we also want to have this, right? The form of the perturbation is proportional to A itself. All right, from that we can see that the retarded correlation function of A delta H T prime, let's say, is precisely the correlation function, the retarded correlation function of A with A T prime. Already I'm gonna write something like this, times this function here at T prime. Why? Well, this function will just factor out of the commutator and also at the expected value. And here, everything that will remain is operator A in the interaction picture at time T prime. Okay, so this is what we have. Now we take the Fourier transform. So I know that I can have CAA omega equals minus infinity dt minus t prime e omega plus, and remember omega plus is omega plus this small imaginary part. We discussed that, why we need that for this Fourier transform to be well defined as well. So this AA retarded at t minus t prime. Okay, all right. So then in this case, we also have the inverse, right? C AA retarded t minus t prime equals minus infinity to infinity d omega e minus omega plus t minus t prime. That, of course, this is omega plus. There's a d omega plus here. C A R omega plus. All right. So we can, given this delta A, we can of course define who's going to be dA of omega is going to be then, now since t0 is going to minus infinity, this is simply going to be integral minus infinity to infinity. There's going to be a dt prime e to the omega plus t prime, let's call it delta A. Yeah, let's not call it t prime, let's call it t. Delta A of t. Okay, this is going to be then e omega plus t integral of this guy, which is going to be integral of, again, right, I'm sending t0 to minus infinity, dt prime of CAA retarded between t and t prime times, or t minus t prime, doesn't matter, times this function t prime times this let's see, yeah, and now I can multiply this by something like that, which is 1 t prime. Okay, so by doing this, we have this, we can say, write it as this. Let's put the integral in dt prime here, dt prime, and then let's do this. It's going to be the integral in t here. I'm going to collect these e omega plus t, e minus omega plus t prime. This is going to be e omega t minus t prime. There will be the CAAR here, tt prime. So this is all for fixed t prime. Then I'll have these other one here, e plus I omega t prime times ft prime. Okay, and this is precisely omega c AAR at omega, right? That's the definition. dt minus t prime, I'm integrating over t, so t prime is fixed here, so this is just dt, the way I'm doing it, right? It's all inside. So here, and whatever is left is the Fourier transform of f times of ft prime, e omega plus, so this is going to be CAAR omega plus f omega plus. All right, so that's my Fourier transform of S omega, and that's retarded, that's omega plus 2. So now the only thing we need is to calculate CAA of omega. By the way, this is called then the dynamical susceptibility, All right, let's go back to the slide. Okay, so we showed that we defined the dynamical susceptibility as this retarded correlation function when B is equal to A. But this is all very abstract, right? So it looks easy enough. If we know how to define the perturbation, then this correlation function follows. Notice that here we had to in order to go into frequency domain, you had to take t0 to minus infinity. So that's one point. But how do you do in practice? How do you even know what that the perturbation has this form? So let's take the example for the case of the charge density, and let's see how that applies into a real situation. And this case is a so-called dielectric response of a system. So let's see how does that work. Okay, so let's consider dielectric response then. And before we turn on the perturbations and do the linear response, let's try to understand what we're trying to do here. So imagine I have a conductor, a metal, and this works even in the classical case where quantum fluctuations are irrelevant. So let's just review that. Basic physics of dielectric function here. So imagine you have a system where you have charges and you apply an external electric field here. So how do you do that? You always have Gauss's law, right? So you have a charge distribution, or I'm called external charge distribution, say positive charge here in this plate, negative charge here, so that creates an electric field in this direction. And you apply here and you have this system, this metallic system here. So what happens when you apply, and you actually might have, electrons in the system. And what happens here is that there will be a polarization within this metallic system. So there will be an induced charge density because I'm applying this electric field. Meaning you can think of this as is energetically more favorable for the positive, to have an accumulation of positive charges here close to these negative charges, and an accumulation of negative charges here close to these positive charges. So there will be a polarization or an induced electric field just because I'm applying this external one, right? So this is like a transient situation, and the system is going to respond to this external field this way. So that's essentially the dielectric response we want to evaluate, right? So and this, of course, after a while, after the transients, say that this was turned on and minus infinity, you get to this situation. All right, so what's the electrodynamics here, or electrostatics here? So you have these induced charge density, right? Which is the difference between the charge density in equilibrium, where everything was uniform, say, and the charge density at t larger than t0 when you apply this external electric field. And that creates this induced electric field. Sometimes this is called it's proportional to minus the polarization, or if you want the dipole moment, but let's call this the induced electric field. So the total electric field felt by a charge in this system is going to be the sum, the vector sum of the external field, which is along this line, and this induced field. So it's going to be something around here. So that's what I'm writing there. So usually in the courses, this is written as, this is the total electric field, which is this, is called the electric field. This external field is called the displacement field. And there you have to relate them by this, the epsilon zero. And this induced field is usually called minus the polarization of the system here. So this is usually what you find in textbooks, right? So that the displacement is epsilon zero times electric field, the total, plus the polarization, usually is written like that. And in fact, this is the one that you're going to write Gauss's law with, all right? So why? Because you have to add these external density, the charge density with the induced charge density to get a total charge density, and so your total potential will also be the sum of these two. And when you write, say, Poisson's law or Gauss's law for that matter, you have to include these two. This one only involves this one. So if you're talking about this electric field here and these charges, you're going to use Gauss's law using D. Okay. And of course, you want to use Gauss's law with this one, you have to use the total and so forth. But what is the dielectric function? Okay, so the dielectric function is the relationship of the total electric potential, right, which is the sum of the ones caused by this charge and this charge distribution, right? So the total. As a proportion of the external one, as a response to the external one, right? So this is usually referred to as the dielectric function. In the isotropic, so if this doesn't depend on position, say, and you can and this is linear. This might not be a tensor, for instance, where this is D and E are at the same, are proportional to each other. They're in the same direction. This is not always the case. Like here, it's definitely not, but it could be, right? Then you would have this expression. And sometimes this is not called sometimes this product is called the dielectric constant. This is called something else, sometimes called the relative permittivity of the system. But here, what I'm calling the dielectric function is this. You might call it relative permittivity if you want, okay? But this is what I'm talking about. But here I'm allowing it to depend both on time and on position, okay? So this is what I want to calculate, right? The response from these external perturbation and how it affects the total potential. Okay. So let's treat now what I'm calling the perturbative quantum limit. And by quantum limit, I mean the following: that we're going to consider the electrons in the system to be quantized, if you want. So we treat them as quantum particles. The fields themselves are not going to be quantized. So we're not talking about photons here, just considering classical fields. But the density of the electrons, for instance, is going to be this psi dagger psi. So this is like the density in at a position r. So right, psi dagger counts the number of electrons at a position r, psi dagger psi, and I multiply by minus e so that I have a charge density here. So this is my charge density, quantum charge density. And again, at that time t0, I turn on this perturbation, which is a classical perturbation, right? Just a classical field. And I'm not, interested in quantum fluctuations for the fields here. But the net effect is that I'm going to induce a charge distribution in the system at a given time t, and this should depend on time, but would be then the expected value of the charge operator at a given position r, right? The charge density operator at a given time t minus the equilibrium case where it happens, where I had before I applied this perturbation. All right. And this, of course, given that I have this external field here, this will give me a change in energy, right? Charge density times a potential, electric potential, will give me a energy density here that if I integrate over the entire space will give me a contribution to the Hamiltonian, or a change in the Hamiltonian. Notice that this will depend on the charge itself. And the charge here is precisely what I'm calculating the expected value to get the induced charge. So the question that we want is, what is the response of this induced charge, or the expected value of the density at a given time t minus the equilibrium value, given that I'm applying this particular field here. And we're going to see that if you apply linear response to this guy, that we're going to have a charge density correlation function here, and that's going to be our response function. So let's see how does that work in the blackboard, and see how we get this to this expression. Okay, so this is the response function. This is then what I'm calling delta. Let's call this delta, expected value of the charge at a position r as a function of t. And from linear response, we know that this should be rho e r. There's an r here that a little bit different. So it's going to be the integral from t0, say, dt prime, let's call this dt prime, of the following correlation function, minus I retarded t minus t prime of the expected value between this a, right, and delta h, the function of time. This is at time t. This is again written in interaction picture, okay? And this is going to be, well, remember it's in interaction picture. I'm going to omit here, otherwise I'll be keeping these indices too much. So, and this is also an integral in R. So let's call this an integral in, since I'm using R here, let's call this R prime of what? Of this at R prime, the same density operator, the density, times, and of course this will eventually the external field at R prime and at T prime, because this is evaluated at T1, okay? So then commutator, that's it. All right, so again, let's do this. Let's put these two integrals here, T0, let's put this minus I here out of the way. There's going to be this theta t minus t prime. There's going to be a dt prime here. There's going to be this integral in R prime, okay? Yeah, let's already put this in there. Yeah, let's do the whole thing. Why not? Let's do this. dt prime. There's dr prime here, also an integral. And what I'm going to be left with is this, minus I theta t minus t prime of the correlator of rho e times t and rho e at position r prime times t prime, commutator, times phi x at r prime t prime. And this is what I'm calling the associability, the dynamical associability for charge. Okay, let's call this rho e, and depends on r and t, and r prime and t prime. So this is, of course, a retarded function, and a retarded function, so that's what I'm calling here. And this is, of course, the induced charge. So I have the rho induced of r equals an integral t0 dt integral dr prime is rho e rt r prime t prime phi external r prime t prime. That's what I had in slide. So let's go back to the slide and take another look. Okay, so we got to here. And now what we want, remember, is the response function, the dielectric constant, which is this, one more, oops, sorry. One more, there. We want to associate the total potential with external potential. We already did have at least this density related to the external potential is a first step. So let's try to calculate the dielectric function. And just as an initial comment, sometimes this density correlation function that we're defining here is called the polarizability. So let's see how we can calculate the electric function. So the first step is to remember that we can write Poisson's equations given the induced charge distribution to obtain the induced potential, right? This should be all linear here, so we can in principle integrate that by using yet another Green's functions. The Green's functions for the case where this is a delta function, right? And we know how to solve that. These are like a classical Green's functions, and when this is a delta function, the Green's function is the Coulomb potential. So we can solve this as an integral equation like this. So yet another application of Green's functions here, but has nothing to do with our retarded and advanced Green's functions, just a comment. All right, so this is the formal solution. If we know the Coulomb potential, we know this induced density, we can calculate this. But of course, remember you want to calculate the response, this guy here. And we already have this intuition that is going to involve somehow this density correlation function that we calculated in the previous slide. So let's go to the blackboard and see how we obtain this expression, why you have these delta functions here, and why you have the Coulomb potential appearing here. Okay, so I found a typo here in the previous expression. I had the induced potential is, in terms of the Coulomb potential, is integral over R1 UR minus R1, the induced charge density at R1. Okay, so now I want to express this dielectric function in terms of the correlated expression that we had here. So in order to, we already have the induced charge density in terms of the external field, and we want then to write this in terms of the phi x, so that we have phi thought in terms of phi x. So let's just do this quick calculation here. So phi thought at position r time t equals phi x at position r times t plus this integral. I'm going to write at r2, okay, because I already have an r1 there, so I'm going to keep that. R minus r2 times what? The induced charge at position r2 and time t. So this is going to be r2 here, right? So there's going to be another integral, dr1 dt1 chi at r2, but still at time t, right? The time remains the same. r1 t1 external potential at r1 t1. Okay, all right. So this is r1 t1. Now I'm going to write this guy like this: an integral over dr1 dt1, a delta function r minus r1, and a delta function t minus t1 times this at r1 t1. So, and I'm gonna just delay a little bit so that I'm gonna write these other terms and multiply everything by phi x at r1 t1. Okay, then I'm gonna have this dr2 u r minus r2 times the correlation function er at r2 t r1 t1, and all of this is multiplied by phi external of r1 t1. Okay, from here we already get who should be this epsilon minus 1 of rt r1 t1. Okay, it should be it, everything that is in here, which then allows us to write this dielectric response in terms of r1 t1, right? And then this is, of course, phi thought at r and t, and we get the first expression there. So let's go to the slide. All right, we're back to the slide, and I correct that typo that I had here, and we get to the expression we just derived. And now I want to do a Fourier transform, which is valid for translation invariant systems. So we write this not only in terms of the frequency, but in terms of momentum. And this is something that we're going to start doing in general. So the dielectric response is usually cast in this form, right? 1 plus u over q times the response function, the correlation function as a function of q and omega, which is defined as I mentioned, as a Fourier transform both in time and in space. Notice that in space there's minus iq, r minus r prime, and this is, as I mentioned, is valid for translational invariant systems, so that this will only depend on the difference between, say, r2 and r1. And once we do these two Fourier transforms, we get this expression, which is how it is usually referred to. So let's go to the blackboard and do this quickly, so that you know how to do this Fourier transform. All right, so we're back to the slide. So we want to do a Fourier transform in both time and space. And as I said, the Fourier transform in space would work something like this. So if you have a function which is depends only on the difference in position r and r prime, you can define a Fourier transform by integrating this over e to the minus iq dot r minus r prime over dr minus r prime, and this is your Fourier transform in Q. Okay. Now, of course, if this is a delta function, right? Of course, this will be 1, right? Same thing for, well, for the, if you have a function that's, let's call it something, well, we defined the Fourier transform for delta t minus t. 1 is also, should be 1 when you Fourier transform it, all right? So this part, when I Fourier transform this both in either in space or in time, I should get 1. So the 1 comes from there. Now this one's a little bit tricky. So let's see how does that work. So in principle, we have this function, this thing is a function. Let's call it a function of r and r1, right? An invariant system, that's what we're integrating here, is what? Is this integral of the r2 ur minus r2 times this correlation function, which will be a function of r2 minus r1. Notice this, right? t1 and t minus t1 d, and that's the function. Oops. So let's now do the Fourier transform of this. So one thing that we can try to do is write this as the inverse Fourier transform of this guy. So let's try to do that. So this would be an integral in dq of e plus iq r minus r1 of fq integrated. So this would be the inverse transformation of this guy. So let's see how we can do that. We can, of course, still write this as dr2 ur minus r2, and this let's write as the inverse Fourier transform of xe of rq, which would be dq e plus iq, now r2 minus r1, right, because that's the argument here, of chi e of r q at t minus t1. Okay, now notice this. Let's do another step here. This thing here. Okay. Let's put the dq here, and I'm going to write r2. Yeah, let's put it in another color. These R2 I'm going to write as R2 plus R minus R. essentially because I want the same factor as in this left-hand side. Okay, so this would be dq e plus iq r minus r1, and now I'm left with an integral in r2 of u r minus r2 with e of plus I q r minus r2, right? So I had this, the r minus r1 is there, so I have r2 minus r with a plus iq. Yeah, oh, sorry. So this is, let's just add one more line here, and this is r r2 minus r, just so that we are on the same page here, minus r1, and this is equal to r minus r1, r minus r1 plus r2 minus r. Okay, this is plus, and this is going to be r2 minus r here. Or if you want r2 minus r times what? Times t minus t1. Okay? Now notice that this is also equal to u of q. Well, because this is dr2, so this is how we define it, right? Or dr2 u of r minus r2, and if that only depends on the absolute value of this would be something like that. Might depend on the orientation, but if it doesn't depend on the orientation, it will be just r2 minus r e plus iq r minus r2 minus r. Okay, that would be my r2 u over q. That's how I define. So the end result here would be integral over dq, and let me just write a little bit more, I q r minus r1 times u of q times ker q t minus t1. All right, so the Fourier transform of this is precisely u of q times the correlation function at q, where I define this precisely as in this form with an important difference here. The definition for the Fourier transform for u has this plus sign here. Okay, this is crucial. There's a plus sign here. So where u over q has this plus sign, r2 minus r there. Okay, r2 minus r, this is what I'm calling u of q. Now the second part is just to Fourier transform in frequency, but that's trivial because, right, so this already gives me the Fourier transform in Q, in frequency B, just applying this, and I'll get just this as sine of omega. So that's how we get to the final result that E minus 1 of Q and omega is 1 plus UQ P R E Q and omega, right? The tricky part is to get the U of Q, and there's this definition here. So let's go to the slide and finish this. Okay, so just to finalize, we have this final expression for the dielectric response. If this is the pure Coulomb potential with no screening, nothing, U over Q depends on Q as Q 1 over Q squared. You can calculate this. Probably it will be one of the assignments. And notice that the plus sign here, while here in the Fourier transform in Q, I have e to the minus Q, all right? So this is then the dielectric response calculated in linear response. And in the next class, we're going to look at the conductivity tensor and do a similar calculation there. All right, that's it for this class. I'll see you next class.